Good evening, everyone. So, I welcome you all to the live interaction session 6 for the NPTEL course Fluidization Engineering. The course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. And this is Sayinkar Kartiga, a research scholar from the Department of Chemical Engineering, IIT Hyderabad, handling the live session. So, the course theory would be covered by the course instructor and the live interaction session or the problem solving sessions are just aid for you people to help solving the problems associated with that week's lecture. So we'll start off with this week session. Yeah. So before starting off, we'll just have a quick intro on the course layout. That is, what are all the things we have covered and what are all the things that we will be covering. This is just a quick recap of things. We have seen this in previous class also, but just for those who are attending the session for the first time, just for giving a nice intro to them, this one is repeated, so please bear with me. So in the first 2 weeks we saw the introduction to the phenomenon of fluidization. And what is fluidization? It is a phenomena that is happening when fluid is passed inside the packed bed at a sufficiently higher velocity so that the particles inside the packed bed starts behaving like a fluid. For example, uh, we have a column of or a glass of water. If we tilt the glass, what happens? The water tries to maintain its level, uh, like it tries to maintain the level by adjusting its flow with respect to the glass, right? So in this fluidized bed the similar thing happens. That is, if we incline or orient the fluidized bed at a specific angle, the particles or the bed starts leveling up with respect to the altitude. So it has the fluid like behavior. It starts moving like a fluid rather than staying put or staying contained in a as a solid. So what would be the advantages? The advantages are such that the heat transfer rate and mass transfer rate are completely improved, because in packed bed there are chances of hotspots forming, whereas in fluidized beds those things are rectified. Those things are rectified in the aspect that the mass transfer and heat transfer rates would be so uniform and it would be better. And disadvantages would be such that when we are dealing with catalysts, there are chances of those catalysts, because of its movement, for them to erode. So these are all the disadvantage of fluidized bed. And also, if we cannot use for costly materials. And industrial applications of fluidized bed, it is widely used for various techniques like polymerization, fluid catalytic cracking, biomass gasification, and so on. So in industries, fluidized bed is a widely used technique. So this one has a very high amount of uh, applications as well. So studying fluidization engineering is a very good choice, because it would be helpful in if you are in BTechs or MTechs, it would be an additional update to your profile in terms of getting noticed, because it is one of the thing that is widely used in industries. And week 3 we dealt with characteristics of solid, classification of solids, flow characteristics and its outline in different types of fluidization. So particles can be classified into 4 categories according to Geldart's classification. He characterized the particles based on their density difference and the diameter of the solid particles into 4 categories. The very smallest one comes under Geldart C, because they have additional forces, like they would be cohesive in nature and it is very difficult to fluidize those particles. And the next one comes as the gel dot A particles. Gel dot A is comparatively larger than gel dot C, and it is easier to use in fluidized bed, where it is used in various industrial applications too. And next comes the gel dot B particles. It is the preferable one, whereas but only the one disadvantage is that it leads to bubble formation. And the last category is delta D particles. These are very largest particles and it is very difficult to fluidize them, but it is ideal when we are dealing with spouted fluidized bed. So all these characteristics of solids and classification of solids were dealt in the week 3. And in week 4 or week 5, we dealt with the flow pattern of fluidization system. When we increase the velocity, the packed bed gets transformed into fluidized bed. But what are all the stages it undergoes? For example, if we are dealing with the liquid solid fluidization, the chances are that the particles would be smoothly fluidized. It is known as particulate fluidization or homogeneous fluidization, because there would be no bubble formation that would be occurring in those systems. Whereas when we are dealing with gas solid systems, it progresses through a series of steps. The first one being bubbling fluidization, and the next one is the slugging fluidization and turbulent fluidization. In all these things, what happens is that the bubble starts forming and the bubble starts to grow with increase in the fluid velocity, which once it crosses some threshold value, its bubbles burst and there is a huge amount of turbulence occurring inside the system. So all these are seen, and how to map them according to their diameter and the velocity was also seen in those classes. And frictional pressure drop and its models to analyze small solid movement, mixing, segregation, and staging. And the next is the week 6 is gas distribution, types of gas distributor in small and large scale industries, design of distributor. This we was a portion of last week where we saw a different type of gas distributors for gas solid systems like porous distributor, perforated distributor, and tube type distributor, and sparger or internal uh, type distributors also seen. And what would be used when was all dealt in the last class. And this week we would be dealing with bubbling fluidized beds, gas dispersion, gas interchange in bubbling beds, mixing characteristics. So then this week and the next week, the main objective is to learn completely about the bubbling fluidization that is mostly happening with the gas solid system. And followed by that, we would be dealing with entrainment and illustration from fluidized beds, which are nothing but the solid carryover, and attrition mechanism and its analysis by model. And 10 to 11, week 10 to 11, it major focus is on mass transfer happening inside the fluidized bed from particle to gas or particle or whatever it is, and its analysis by model in 2 and 3 phase systems and modeling. And the last week we would be dealing with heat transfer phenomena that is happening inside the fluidized bed, and the various design criteria, design for physical operation, catalytic and non-catalytic systems. So these are the topics that will be covered in these classes. So the problem solving session's objective is to make you people understand the problems that can be arriving out of the theory that is taught in that week's portion. So mainly it would be dealing with a few assignment problems or sample problems or whatever. If you have any suggestions, please let us know so that it would be incorporated in the coming up weeks. And the books and references for this course is that the first one is the Cooney and Levenspil's Fluidization Engineering, which is a very good book which you can completely rely upon for understanding the basics of fluidization phenomena. And next is the Gidaspo's Multiphase Flow and Fluidization, which has continuum and kinetic theory description. The continuum and kinetic theory description is nothing but generally we know the solids particles behave as a solid and the fluid is gas. For gas, we have kinetic theory of gases. But how do we account for the motion of the solid particles? We have to define something, and that something is the kinetic theory of granular flow, which comes from considering the solid particles to behave as a fluid. So in such cases where the solids are in complete motion, they are assumed to behave as a gas molecules, and the theory is framed accordingly to get some description for certain parameters of the solid phase. So it is well explained in Gidaspo's book, and third one is Gibilaro's Fluidization Dynamics, and fourth one is Professor S.K. Majumdar's Hydrodynamics and Transport Processes of Inverse Bubbly Flow. So now we'll go to uh, this week. This is week 6, and the main focus, as I have said, is about bubbling fluidized beds. So what happens? Yeah, what happens inside a fluidized bed? Fluid passes inside the bed, and the bed would be packed. So depending on the fluid velocity, the particle starts to move, and this is the arrow representing solids movement in the bubbling fluidized bed. So A and B are nothing but shallow beds. These are not shallow beds but equal height. That is, this Z and dt is Z and dt are in equal proportion. That is, Z by dt is equal to 1. In such cases, like a square bed, typical square bed. In such cases, when the velocity is very low, we have the solid circulation pattern as this. That is, the particles arises near the wall and it falls down near the center. Whereas this pattern is completely reversed when we are dealing with a higher inlet superficial gas velocity. So that thereby the particle starts arising from the middle and it falls down near the walls. And this is for low velocity and high velocity, which is given over here. If the bed height is increased, so that z by dt is equal to 2, and higher velocity, we have the circulation pattern similar to this, where the particles go towards the center, and from there it gets split into two portions. And these two are shallow bed, where here the fluid distribution is very uniform, and in such cases, as you can see, the particles keep circulating like this. Whereas when there is tears for gas inlet, you can all see how it affects the solid flow pattern. Here it goes straight, whereas the near in between space, they are going in circulation type. And this is a general pattern in deep fluidized beds, whereas it is observed that the solids arising near the walls and it moves towards the center and goes to the topmost region. From the topmost region, they are pushed back into the bed, and this is the general pattern inside the fluidized bed in deep beds. So the next, these are the circulation pattern inside the bubbling fluidized beds. So now we'll go on to see. Now we'll go on to see the problems for this week's session. So the first question is that the thumb rule for pressure drop across distribution is where delta PD and delta PB are pressure drop across distributor and pressure drop across distributor bed. Delta PD is nothing but pressure drop across distributor, and delta PB is nothing but pressure drop across the bed. So what is the delta PD? The general thumb rule, what does it state? So the first one is delta PD is equal to 0.2 to 0.7 delta PB, and the option B is 0.2 to 0.4 of delta PB, and option C is 0.5 to 1 of delta PB, and option D is 1 to 2 of delta PB. The right answer is delta PD is equal to 0.2 to 0.4 times of delta PB. So the answer is option B, that is delta PD is equal to 0.2 to zero point 0.4 of delta PB. Now we'll go to question 2. In question 2, it's asked that at a very low gas flow rate, the frequency and size of bubbles formed are primarily governed by surface tension of the liquid, buoyancy force of the bubble, both A and B, none of the above. So what happens when bubbles form? Basically, surface tension force forms a major role in protecting the bubble size and its formation. So, at a very low gas flow rate, the frequency and size of the bubbles formed depends on the surface tension of the liquid, and also the buoyancy force of the bubble naturally plays a role in these type of things. So the answer to this question is option A and B. Option C, which includes both option A and option B. So the right answer is option C. We'll move to question 3. In question 3, it is given that bubble formation in a fluidized bed is very similar to that in inviscid liquid, viscous liquid, boiling liquid, all the above. So, what does it mean by, we know what a boiling liquid is, and we also know what viscous liquid is, but what is inviscid liquid? Can anyone answer this actually? It is like, viscosity is not an important factor. So that is in the inviscid liquid flow. So bubble formation in a fluidized bed is very similar to that in an inviscid liquid where the viscosity effect is neglected. So the bubble formation is very similar to that in that invisible liquid. Above the critical Froude number, jets are present in a fluidized bed. Bubbles are formed in a fluidized bed, both A and B, none of the above. Above the critical Froude number, jets are present in a fluidized bed. Bubbles are formed in a fluidized bed, both A and B, option C, none of the above. So what does critical Froude number mean? The answer is bubbles are formed in a fluidized bed. So Froude's influential paper of 1861 was published by the Institute of Naval Architects. Froude had surmised that to predict the behavior of a ship moving through water, he would need to experiment with much smaller versions of ships or models that could be scaled to the behavior of much larger vessels. Thus, Froude number was derived from experiments with model boats a few meters long. So, what happened is that in 1861, Froude had published a paper in the Naval Institute of Naval Architects where he wanted to analyze the ship behavior moving through water. So he wanted to experiment with smaller versions of ships or models that could be scaled to the behavior of much larger vessels. So Froude's number was derived from experiments with model boats a few meters long. The number expresses the characteristics of flow, including surface waves and bed forms, as the ratio between gravitational force and inertial force. So the Froude number is given by this, where it is V by root of G into D. Here it represents nothing but V is the velocity and D is the diameter of the vessel or something. Flow dimension. The number expresses characteristics of flow in that, including the surface waves and bed forms. It is nothing but the ratio of gravitational force and the inertial force. Where V is the bulk flow velocity having the dimensional units LT inverse, and that reflects the dominant effect of gravity on surface flows, and the inertial compound is G into D, where G is the gravitational constant and D is the water depth. The denominator represents the speed of a surface wave related to the bulk fluid velocity. That is, V is the bulk fluid velocity and G into D square root of it gives the speed of a surface wave relative to the bulk fluid velocity. If the the whether the surface wave is faster, slower, or same speed as the bulk flow will depend on its resistance to move or its inertia. Thereby, Froude is dimensionless. The numerical value of Froude is used to define three conditions of flow. If Froude is less than, or Froude is equal to 1, any surface wave will remain stationary. It will not move up or down. This conditional occurs when both the velocity and water depth are at critical values. Not surprisingly, this condition is called as critical flow. If Froude number is equal to 1, it is known as critical flow. It is the formation of stationary waves above and usually in place with the antidune bed forms. And when Froude is less than 1, inertial, as you can see, this is gravitational force by inertial force, right? If it is less than 1, the inertial force dominates and the result is a subcritical condition. Tranquil flow. This corresponds to lower flow regime bed forms such as ripples and large dune structures. If it is greater than 1, gravitational force dominates, resulting in supercritical flow condition. The corresponding stream flow surface conditions manifest as an acceleration of flow such that the stationary waves break upstream. As you all can see, from that we can see above the critical Froude number, either jets are present in a fluidized bed or bubbles are formed in a fluidized bed. Above, it is giving that Froude greater than 1, that is critical number is 1. So greater than 1, gravitational force starts dominating in the supercritical flow condition. The corresponding stream flow through the conditions uh, manifests as an acceleration of flow such that the stationary wave break upwards, break upstreams. So the water, the bubble forming and growing and getting dissected or something is seen when Froude is greater than 1. In question 5, it is given that the ratio of specific heat of gas is Cpg by Cvg. Ratio of specific heat of gas is dash, where Cpg and Cvg are the specific heat capacity of gas at constant pressure and constant volume respectively. So I don't think we need an answer option to this question. It is given that the ratio of specific heat of gas. We all know that ratio of specific heat of gas is gamma, where that gamma is given by gamma is equal to Cp by Cv. We'll see what the options given are. Cpg by Cvg, Ctg by Cvg, Cpg by Cv, Cg by Cvg. So basically the first one is Cpg by Cvg. So it is a gas at constant pressure it is Cp, and at constant volume it is Cv. So Cp by Cv gives us ratio of specific heat of gas. Answer to this question is option A. Option A, Cpg by Cvg is the right answer. We will now move on to question 6. In question 6, it is given that in the case of a stream of bubbles in a vertical tube generated continuously by blowing air in the bottom, the peak velocity at the middle of the bed is about 0.5 times the average velocity, 1.2 times the average velocity, equal to the average velocity, none of the above. So imagine a condition where bubbles are generated by blowing it into the blowing in the air at the bottom. So what would be the peak velocity at the middle of the tube? Either it is 0.5 times the average velocity or 1.2 times the average velocity. So the right answer to this particular question is that when the velocity, that is average velocity, one is 1.2 times the average velocity. The peak velocity at the middle of the bed is 1.2 times the average of the velocity. We'll now go on to question 7. The bubble velocity is affected by the presence of the vessel wall when the bubbles are large enough to exceed approximately 25% of column volume, 15% of column volume, 10% of column volume, 10% of column diameter, or option D, all the above. So bubble velocity is affected by the presence of the wall, surrounding wall, right? So when this happens when the bubbles are large enough to exceed approximately 25% of the column diameter. We need to have a set of standards put forward. So bubbles are large enough to exceed approximately 25% of the column diameter. We'll move to question 8. In question 8, it is asked that the wall effect becomes negligible only when the equivalent bubble diameter dB is less than 0.1 of the bed diameter, more than 0.1 of the bed diameter, equal to the bed diameter, or all the above. What is asked here is that we have a equivalent bubble diameter dBE. What happens if it is equal to the bed diameter? The bubble would be almost occupying it totally. The wall effect is much more, like it can get stuck in that. Or if it is more than 0.1 times the bed diameter, again the same thing. Or if it is less than 0.1 times the diameter of the bed, then that is the right answer, because only in those conditions the wall effect becomes negligible. We'll go to question 9. A gas stream is compressed by an adiabatic reversible compressor from pressure 1 atmosphere to final pressure 10 atmosphere at room temperature 20 degrees Celsius through a fluid bed system. What is the outlet temperature given the ratio of specific heat as 1.33? Actually, a similar question was somewhere else, that's why I'm searching for it. In question 9, it is given that a gas stream is compressed by an adiabatic reversible compressor from pressure 1 atmosphere to final pressure of 10 atmosphere at a room temperature 20 degrees Celsius. What is the outlet temperature if the ratio of specific heat capacities is 1.33? So the given option is option A, 527.63 Kelvin. Option B, it is 456.32 Kelvin. Option C, it is 308.56 Kelvin. Option D, it is 263.47 Kelvin. So we'll just solve this one. And yeah, what is the outlet temperature? We'll solve this, no issues. Question 9. P1 is equal to 1 atmosphere. P2 is equal to 10 atmosphere. equal to 20 degrees Celsius, 293 Kelvin. Oh, sorry. What else is given? Specific heat capacity is given. Gamma, yeah, is equal to 1.33. So, what is the thing that we need to be calculating? We need to find the T, sorry, T2 is equal to P1 by P2, T2 by. So we'll substitute everything over here and we'll see what it is. T1 is 293 into 10 by 1. I mean, the unit conversion doesn't matter here because we know everything. 0.33 minus 1. I mean, P2 by P1, since it is in the ratio, it doesn't affect much if it is if we don't change the unit. So what does this give? equal to we have 293 into 10 0.33 divided by 0.33 0.2481 is equal to 10 power 0.2481 2481. It is 293 into 1.7705 is equal to 93 518.76 Kelvin. So we'll see what are all the options that are given. The closest one that is coming out for us is 527.63 Kelvin. So the answer is option A, 527.63 Kelvin. What would be the thing that would have gone wrong here? I'll just do the calculation again and come. 1.33 minus 1 divided by 1.33 0.2481 10 power answer into 293. Yeah, so the answer is 527.63 Kelvin. What is the outlet temperature? Given the specific heat temperature, specific heat as 1.33. So we'll go to question 10. In question 10, it is asked that the bubbles in fluidized beds grow in size due primarily to the factors effective hydrostatic pressure decreases towards the top of the fluidized bed. Bubbles coalesce in the vertical direction with the trailing bubble catching up the leading bubble. Bubbles coalesce in the horizontal direction with the neighboring bubbles. All the above. So what happens? Effective hydrostatic pressure decreases towards the top of the fluidized bed. That is true. And bubbles coalesce in the vertical direction also, whereby the trailing bubble moves forward and catches up with the leading bubble, and also in the horizontal direction with the neighboring bubbles. In all the directions, bubble coalescence takes place. So the answer to this question is all the above. The fluidization behavior of the powders was independent of both of the mean particle size and of particle size distribution for Option A, group A powders. Option B, group B powders. Option C, group C powders. Option D, all the above. Fluidization behavior of the powders was independent of both the mean particle size and of mean particle distribution for group B powders. So the answer to this question is option B, that is group B powders. And we'll move to question 12. In question 12, it is given that the mean bubble size in a fluidized bed is found to be dependent on type of distributor, distance above the distributor plate, excess gas velocity above that required at the minimum fluidization condition, all the above. So in this question also the answer to this is all the above, because we have seen that how mean bubble size depends upon the gas distributor, that is the gas distributor types of porous, perforated plate and nozzle tubes. How different gas distributor system form different type of bubbles was studied in the question 12. Sorry, was studied in the last week's problem solving session itself. How different type of distributor influences the particle motion inside the bed. So type of distributor is one of the option, and distance above the distributor plate in turn affects the jet formation or not. So again it mean bubble size, it affects the distance above the distributor plate, and excess gas velocity above that required at the minimum condition, and all the above, like how much it is excess only then that forms into bubble. This is one of the theory. So excess gas velocity above that required the minimum fluidization condition, this is one of the option. So the answer to this problem is option D, that is all the above. In question 13, it is given, according to Mori and Ven's model, maximum bubble size depends on relative velocity of the gas to the minimum fluidization velocity, cross-sectional area of the bed, both A and B, none of the above. According to Mori and Ven's model, which gives dB max, if you could remember, it comes along with the cross-sectional area of the bed, that is uh, bed, bed cross-sectional area, and also the relative velocity of the gas to the minimum fluidization velocity. So only then we can get to know how much excess gas is present than required at the minimum fluidization condition, so that leads to the formation of bubbles. So the answer is option C, that is both A and B. For porous plate of H naught, which is a characteristic of the distributor plate, should be equal to. For the porous plate, the value of H naught, which is the characteristics of the distributor plate, should be equal to H naught is equal to 0.5, H naught is equal to 1, H naught is equal to 1.5, H naught is equal to 0. So the answer is, for the porous plate, H naught should be equal to 0. It should not be equal to 0.5, 1 or 1.5. Rather, H naught should be equal to 0. So question 15, the catchment area of a distributor plate is defined as the area of the distributor plate per hole, total area of the distributor plate, half area of the distributor plate, all the above. So the right answer is, what is the catchment area? It is the area of the distributor plate per hole. So how much area it is available for the for one each of it. It has numerous holes in the distributor plate. So how much area or the opening each of the holes has is given by the catchment area. So the right answer is option A, the area of the distributor plate per hole. We'll just take a 5 minutes break before resuming this session. So we'll start after 5 minutes. Yeah, thank you. So in question 16, we'll start the session. So in question 16, it is given that if the bubble grows to the size of the vessel diameter, the bed becomes bubbling bed, slugging bed, stratified bed, none of the above. So if bubble grows to the size of the vessel, the bed becomes a slugging bed. This one we have already seen in the previous things also. So the right answer is bed becomes a slugging bed. In question 17, it is given the coalescing frequency per unit volume inside a fluidized bed is proportional to diameter of spherical bubble, square of the diameter of the spherical bubble, cube of the diameter of the spherical bubble, none of the above. So answer is it is actually the coalescing frequency per unit volume. It is inside a fluidized bed is a formula. It has a formula which is nothing but it depends on the two bubble frequency. I mean two bubble diameters, d1 square plus d2 square. So it's square of the diameter of the spherical bubble is the right answer. In question 18, it is given that for the coarse particles, the minimum bubbling velocity is equal to the minimum fluidization velocity UMF, larger than the minimum fluidization velocity UMF, smaller than the minimum fluidization velocity UMF, all the above. So for coarse particles, the criteria is such that the minimum bubbling velocity is equal to the minimum fluidization velocity, whereas this differs for the spinal particles. The equilibrium bubble diameter decreases linearly with the ratio of volumetric bubble flux to the splitting frequency of a bubble, increases linearly with ratio of volumetric bubble flux to the splitting frequency of a bubble, remains constant with the ratio of volumetric bubble flux to the splitting frequency of a bubble, none of the above. Answer is it increases linearly with the ratio of volumetric bubble flux to the splitting frequency of a bubble. That is the right answer. In question 20, it is given that for the fine particles, the minimum bubbling velocity is equal to the minimum fluidization velocity, UMF, larger than minimum fluidization velocity and smaller than minimum fluidization velocity. All the above. So the answer is larger than the minimum fluidization velocity. So as we can see and distinguish between question 18 and 20, in question 18 it was about the coarser particles. For coarser particles, the minimum fluidization velocity is equal to the minimum bubbling velocity is equal to the minimum fluidization velocity, whereas for the final particles, the minimum fluidization velocity is greater than the minimum bubbling velocity is greater than the minimum fluidization velocity. That is, the minimum fluidization velocity is lower, so minimum for bubbling velocity is comparatively higher. So we'll go to question 21. A shot of gas is injected into a 60 centimeter internal diameter incipiently fluidized bed of 300 micrometer sand, for which UMF is equal to 3 centimeter per second and epsilon MF is equal to 0.5. A 5 centimeter bubble forms. For this bubble, find rise velocity UBR, cloud thickness RC minus RB, volume of wake to volume of bubble FW, that is the wake fraction to the bubble. So just think about this question and analyze. We'll solve this question now. We'll first write whatever it is given in this question before dealing with what to be found. Centimeter, or in other words, 0.6 meter. Incipiently fluidized bed of 300 micrometer sand, for which dia particle and UMF is given 3 centimeters per second, and epsilon MF is also given 0.5. Bubble diameter is again given dB is equal to, okay, B 5 centimeter. Now to find rise velocity UBR and cloud thickness RC minus RB. This one is nothing but RB is the radius of the bubble and RC is the cloud radius. So we need to find the thickness of the cloud. So it is RC minus RB. And volume fraction on of wake. That is volume of wake to volume of bubbles, FW. We have given the initial things, that is given condition, and what we need to find is mentioned over here. So stepping into the problem, this one is nothing but the formula page. So the first thing is we need to find the diameter of bubble to the diameter of vessel. We'll keep it as dt rather than d vessel. We'll keep it as dt. So first we need to find dB by dt. Question 21. We are dealing with solutions. What was dB is 5 centimeter and dt is 60 centimeter. Okay, here we are given everything in meters. So again 300 into 10 minus 6 is equal to 0.03 is equal to 0.05. So the first step is dB by dt. It is nothing but 0.6. Okay. dt is 0.6, dB is 0.05. 0.05 divided by 0.6. So guys, please take a pen and paper and solve alongside me so that it would be easier for you when you are dealing with the same problem in the future. 0.05 divided by 0.6. It is nothing but 0.0833. So what we need to find, it is just a key. It is less than 0.125. So it is nothing but just a criteria for enabling us to use a certain formula, which is nothing but this one. So if this criteria is fulfilled, what we can do from this is we can find the bubble rise velocity. So bubble rise velocity UBR is given by this formula where it is 0.77 and G. We need to use the formula in centimeter. Centimeter. So G is 9.81 meter per second square. If it is in, it is 981 into dB is again 5 centimeter. So it is 0.5 to the power of 0.5. What do we get from here? 981 into 5 divided by 0.5 into 0.77. Sorry guys, there is a small typo over here. It is not 0.77, it is 0.7. So this one gives us the value of 49.02 meter per second. Now we need to find RC cube by RB cube, which is given by this formula. That is for 3D bed, this is the formula. So from this we need to find RC cube by RB cube. So we'll substitute everything in this. So we know the UMF is, what was the UMF again? It was 3 centimeter. Since we are using everything in centimeters, we'll continue with that. So this is equal to UBR is 49.02 plus 2 into 3 divided by UBR is 49.02 minus 3. What does it give? For 55.02 and 46.02 divided by 46.02. 5.02 divided by 46.02. It is giving us 1.1956. So RC cube by RB cube is equal to 1.1956. Now next we need to find we know the diameter of the bubble, right? RC cube is equal to 1.1956 into RB cube. This is nothing but 1.1956 into RB is nothing but 5 by 2. power 3. So it is again 1.1956 into 2.5 cube. It is 18.813. If that is the case, then RC is equal to 18.6813 power 1 divided by 3. Equal to 2.6533. We'll see whether that is the right answer. Yeah, we got 0.49, something, so again it's okay. So RC minus RB, cloud thickness is given by R RC minus R, so which is nothing but RC is 2.6533 minus 2.5 is equal to 0.15, okay, 6533 15533. What else is remaining? What we need to find? They have found out UBR, RC minus RB, and volume of wake to volume of bubble. For that we need this chart. In this chart it is given that for the particle diameter FW is given. So as you can all see from this slide, the diameter of the particle for our case is nothing but it was 300 micrometer. So on crossing this path at 300 micrometer for the natural sand, we are getting somewhere around here. Okay, we can drop a text actually. Insert shape round. So it is 300 microns, so it is coming somewhere around this. So volume fraction, that is the volume of wake to volume of bubble, is given by this, that is 0.24. This one we have got from the figure, so the answer is 0.24. Just quickly go through the steps once again. I'll give you people 2 minutes time. If you have any doubt, please ask. Now we'll come back, we'll go to question 22. In question 22, it is asked that estimate the size of bubbles forming above the following distributors in a bed where U naught is 15 centimeter per second and UMF is 1 centimeter per second. So the first one is porous plate and the second one is perforated plate with triangular array of orifices having 2 centimeter pitch. So first what should we do? We should write given things. Um, Size of bubbles forming above the following distributors. U naught is equal to and UMF is equal to given. So the first one is we should write given, control B, given U naught is equal to 15 centimeter per second. UMF equal to one centimeter per second. What was asked? Size of bubbles. To find for porous plate perforated. The formula for the same is given in this slide. So we'll go over step by step manner. Question 22, question 22. Solution. Slide. Question 22, solution. So the first thing is formula. This is for porous plate. And this is 2.78 by 981 into, it was 15 minus 1 . Okay, the first one is, it is giving us 0.5554 centimeter. Next comes the perforated plate. So the formula for the same is given by this. Question 22 solution. So it was asked about triangular array. So the right thing is triangular array. 2 centimeter pitch is given. So LOR is equal to 2 centimeter. So NOR is equal to 2 by so this would give us 3 into 4 and 2 divided by this. So now we found out number of holes in the when we are using triangular pitch. So NOR is giving us 0.346 per centimeter square. So with this formula we are going to use dB naught. dB naught is given by this formula where 1 by 3 divided by 981.2. So again this and this into u naught is 15 minus 1 divided by 0.346 divided by zero point 0.4. What does this give? 14 by 346 divided by 0.4. I mean to the power of 0.4 divided by 981.2 into 1.30. It is giving us 1.44 centimeter square. Sorry, centimeter. Is this equal to 1.44 centimeter? So this is a straightforward problem wherein it was asked to find the holes, or sorry, bubble size that would arise out of a porous plate and the perforated plate. So the porous plate formula is given as this, and for perforated plate the formula is given like this, and on substituting everything we would get the desired results. Now we go on to for the last question of this session. In actual operation, a two-stage compressor with frictional losses satisfy which one of the following, where WS actual and WS ideal, or actual shaft work and ideal shaft work respectively. The option 1 is given by this. Uh, WS actual is greater than WS ideal. WS actual is less than WS ideal. WS actual is greater than or equal to WS ideal. WS actual is lesser than or equal to WS ideal. So things to be noted in this question is always actual work done would be more than the ideal work done, because to compensate for the losses occurring in the system. So additionally, frictional losses is given, so we cannot say they would be equal because the efficiency would not be 100% in such cases. So the right answer then is WS actual is greater than WS ideal, but it is not equal to. So the answer is option A. WS actual is greater than WS ideal. So I thank everyone for attending this session. So this one is we covered few problems and more theory questions. If you people have any doubt right now, please feel free to ask, or else we'll close the session by giving us quick recap of whatever we saw in today's lecture. I guess there is no doubt in today's session, so we'll close the session by giving a quick recap of the things we saw today. Yeah. Um, so we saw the circulation of solids inside the bubbling fluidized bed and how different bed geometry gives the different circulation pattern, and also how velocity influences the circulation pattern of the solids inside the bubbling fluidized bed. And we saw the pressure drop distribution, how the distributed pressure drop is related to the bed pressure drop. And we saw how the bubble stability or bubble formation is influenced by the surface tension force and also the buoyancy force. And followed by that, we saw the bubble formation in bubbling fluid and fluidized bed is similar to that of the inviscid liquid, that in the inviscid liquid. For the critical number, we saw how bubbles are formed in a fluidized bed. By this, we saw with reference to the surface waves and bed forms, where Froude number is nothing but the gravitational force to the inertial force. If it is greater than 1, what does it mean? The inertial force is very less, so the gravitational force is very great. Actually, I don't think we need this. Was published by the institute. Proud had surmised that predict the he would need. Since we know that, I'm just removing this because the content is too much. Proud's number was derived from the experiments with model fluidized bed. The number expresses the character including surface waves and bed forms as a ratio between gravitational force and the inertial force, where V is the bulk fluid. This one we know. Dominant effect of gravity on surface flow, and the inertial component is GD. Oh, all these are not necessary. And D is the water depth. The denominator represents the speed of a surface wave. Amplifies the surface. Crowd less equal to 1. Any surface will remain stationary. When Froude is less than 1, inertial forces dominate. Just a minute. I just So we saw about the fraud number, and after that we have seen ratio of heat specific heat capacity where Cp by Cv is given, and in case of streams of bubbles it is 1.2 times larger the average velocity, which is the peak velocity at the middle of the tube, and bubble occupies about 25% of the column vessel when it is large, and it is equivalent diameter is equal less than 1.1 of bed diameter, wall effect becomes negligible. And here was a problem calculating the outlet temperature, whereas ratio of its specific heat capacities are given. And this one we calculated using this formula for because it is given adiabatic reversible compressor. So, and then it was about bubbles in fluidized bed grows coalesce in the vertical horizontal direction, and effective hydrostatic pressure decreases towards the top. And then we saw about these are all theory questions, and in the towards the end we saw two problems. The first one was to find the rise velocity, bubble rise velocity, and the cloud thickness, that cloud diameter minus the bubble diameter, and the volume of the wave to the volume of the bubbles. So this one we saw inside a incipiently fluidized bed, and after this we use these formulae to for the study. And for the volume of wake to the volume of bubble, that is the FW, this fraction, we use this chart. And for the next question was to find the size of the bubbles that are formed in the when using porous plate distributor and the perforated plate distributor. So we have used separate formulae, porous plate and the perforated plate. So from this it can be seen that for the porous plate we obtain the bubble size of 0.56 centimeter, whereas in the perforated plate it is almost doubled, and we not even double, it is 3 times larger, that is 1.44 times, sorry, 1.44 centimeter. So we can see that in perforated plate the bubbles are very larger, but porous plate can only be used in the small scale setup, whereas in industrial scale setup we need at least the perforated plates. And it was about WS actual and WS ideal. Here it is mentioned about the frictional losses. Therefore, the answer is WS actual is greater than WS ideal. It is not even equal to. So the answer is option A. So these are all the questions for today's session. So I thank everyone for attending this week. We'll meet again the next week in the same time. Thank you guys. We'll see next week. If there is any questions, I'll wait 2 more minutes. Uh, so we can discuss that, or else we'll close the session after 2 minutes. Thank you guys.